At the very heart of everything you can see, everything you can touch, everything you are, there's a core with almost unimaginable density and power. We are, of course, talking about the atomic nucleus. And in this explainer, we're going to unlock the secrets of its unstable heart.
You know, the chemistry most of us learn about, things like burning wood or iron rusting, that all has to do with an atom's outer electrons. But today we're going deeper. We are exploring nuclear chemistry, which is all about the really dramatic changes that happen inside the nucleus itself. And believe me, it is a completely different and way more powerful world.
For a long time, the picture we had of the atom was kind of like a plum pudding, just this soft ball of positive charge with electrons stuck in it. But then in the early 1900s, a scientist named Ernest Rutherford put this idea to the test. He fired these tiny alpha particles at a super thin sheet of gold foil, and he fully expected them to just pass right through. And, well, most of them did. But some of them bounced straight back. It was, in his words, as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. I mean, wow. That experiment completely changed everything. It showed us that the atom is mostly empty space, with this tiny, incredibly dense, positively charged nucleus right at the center.
So, Rutherford's discovery opened up this huge new question. If this tiny little core is holding everything together, what happens when it's not perfectly balanced? What happens when that core is unstable? And that right there is where our story really kicks off.
Well, it turns out there's this really delicate dance happening inside every single nucleus, a dance between two key particles, protons and neutrons. And the balance between them is what decides if an atom will stay together forever or if it's going to violently transform into something totally new.
Okay, so to really talk about this, we need a quick lesson in the language of nuclear chemistry. Let's look at this notation for carbon. See that bottom number? That's the atomic number. It's how many protons it has. This is what defines the element. 6 protons means it's always carbon. Now the top number, that's the mass number, which is the protons plus the neutrons. So you can have different numbers of neutrons, which gives us different isotopes, like the common carbon-12 or the very famous carbon-14.
So, here's where it gets really cool. If you were to plot the number of neutrons versus the number of protons for every single known isotope, something amazing happens. A pattern emerges, this narrow band of nuclei that are perfectly stable. Scientists call this the belt of stability. You can just think of it as the ultimate safe zone for an atom's core, where all the forces holding it together are in perfect, beautiful harmony. So what about all the atoms that fall outside this belt? Well, they're unstable. They've got either too many neutrons or maybe too few for the number of protons they have. And their natural solution to this problem is a process we call radioactive decay. It's really just the atom's journey back to that safe zone.
So how does an unstable atom actually make this journey? It does it by ejecting particles and energy. Let's take a look at the main pathways an atom can take to get itself back to a stable state.
First up, we have alpha decay. This is usually what happens with very, very heavy nuclei. To kind of slim down, the nucleus just ejects an alpha particle. And as you can see, an alpha particle is basically just a helium nucleus. 2 protons and 2 neutrons all bundled together.
Let's see this in action. Right here, we have an unstable uranium-238 atom, and it's ejecting an alpha particle. Now look at how the numbers just balance out perfectly. The mass number at the top drops by 4, the atomic number at the bottom drops by 2, and just like that, the atom has changed its identity. Uranium becomes a whole new element, thorium. This is like real-world alchemy, a process called transmutation. Okay, next up is beta decay. And this is where things get really, really strange. This is the fix for atoms that have too many neutrons. In a process that just seems to defy classical physics, a neutron inside the nucleus spontaneously transforms into a proton. And to keep the charge balanced, it spits out a high-speed electron, which we call a beta particle. I mean, just think about that for a second. A fundamental building block of the universe just changed its identity. This isn't your high school chemistry. This is some serious quantum magic.
Take a look at iodine-131, which is often used in medical treatments. It goes through beta decay. Now, its mass number, 131, stays the same, right? Because we just swapped a neutron for a proton. But here's the crucial part. The atomic number ticks up by 1. The element isn't iodine anymore. It has become xenon. It's just nudged itself one step closer to that all-important belt of stability.
So a lot of the time after an alpha or beta decay, the nucleus is still left with some extra energy. It's kind of in an excited state. To calm itself down, it releases a burst of pure energy in the form of a gamma ray. This table here sums up the 3 types of radiation really nicely. Alpha particles, they're the heavyweights. You can stop them with a simple sheet of paper. Beta particles are much lighter electrons, so they're a bit more penetrating. You need something like aluminum foil to stop them. But gamma rays? They have no mass, no charge, they're pure energy, and they are incredibly hard to block. You need thick lead or concrete to even slow them down.
So we know how these atoms decay. But that, of course, leads to the next big question. When do they decay? And the answer is both completely random and, at the same time, astonishingly predictable.
Here's the thing. We can never ever predict the exact moment a single unstable atom is going to decay. But we can predict with incredible accuracy how long it'll take for half of a large group of them to decay. And that predictable time frame is what we call the half-life. It's a unique, constant value for every single radioactive isotope.
This classic curve shows it perfectly. So, you start with 100% of your radioactive sample. After one half-life passes, you're down to 50%. After a second half-life, you have 25% left. After a third, 12.5%, and it just keeps going like that. The decay is so predictable and measurable, it's like the ticking of a perfect atomic clock.
And to make this a little more real, here's a number you might have heard of. This is the half-life of carbon-14. Every 5,730 years, half of the carbon-14 in any given sample will have transformed. And this very specific, unchanging number unlocks one of the most powerful tools in all of science.
Because we understand the unwavering predictability of half-life, we can basically read time backwards. We can use these decaying atoms as a kind of natural clock to figure out the age of all sorts of ancient objects.
Here's how that works. Way up high in the atmosphere, cosmic rays are constantly creating a tiny amount of radioactive carbon-14. This C14 gets mixed into carbon dioxide, which plants then absorb. Then animals eat the plants, and it moves on up the food chain. So as long as an organism is alive, it's constantly taking in new carbon, and it maintains the exact same ratio of C14 to regular carbon as the atmosphere around it.
But here's the key. The very moment that organism dies, the clock starts ticking. It stops taking in any new carbon, and the C14 it already has inside it starts to decay with that super precise half-life of 5,730 years. So, by measuring the ratio of C14 left in, say, an ancient piece of wood compared to the amount in living things today, scientists can calculate exactly how many years have passed since that tree was cut down. It's brilliant.
Now, carbon-14 dating is perfect for things that used to be alive, but it does have its limits. After about 60,000 years, there just isn't enough C14 left to get an accurate measurement. But don't worry, for things that are way older, scientists just switch to other isotopes, like uranium-238, which has a half-life of 4.5 billion years. That's how we date things like the rocks that make up our planet.
You know, this journey of an unstable atom finding its way back to stability is one of the most fundamental processes in the entire universe. It lets us date the past, it powers medical imaging that saves lives, and in the form of nuclear fusion, it's literally what makes the stars shine. It really makes you wonder, what other incredible secrets are still locked away inside the atom's unstable heart?